Welcome to this section where I would like to look at integrating odd powers of sine x and cos x. So we'd like to start off by having a review of some results, identities which we're going to use in the process of integrating these odd powers of sine and cos. So what we would like to review here is the Pythagoras theorem, and so let's start by drawing the axes here. Okay, we have the y-axis, and then we have the x-axis here. And then I am going to consider a point P, okay, in this xy plane, point P, which is here, okay, a distance r from the origin O. This is the y-axis, and we have the x-axis here. Okay, this point P here makes an angle of theta with the positive x-axis, and let us call this vertical distance here. Okay, we call this y, and then we shall call this horizontal distance here, we shall call it r. Okay, so I assume that we know, or we are familiar with the Pythagoras theorem here, which tells us that oh sorry, this is not r, I made a mistake here. I meant to call this x. Okay, this is x, this is x, I'll leave it as that. Okay, so the Pythagoras theorem here, which tells us that the square of the side which is adjacent the angle here, theta, plus the square of the side which is opposite this angle theta, for a right angled triangle, by the way, it's a right angled triangle, equals to the square of the longest side here, which is the hypotenuse. Also, we know that, or I assume we know that the cosine of this angle theta equals to the adjacent, okay, equals to the adjacent side, length of the adjacent side, which is x, over the hypotenuse, which is r. And we also know, or assume we know, that sine of the angle theta equals to the opposite side of the hypotenuse. Okay, so we can make we can go on and make x the subject here, for which x is going to be equal to r times cos theta, and then we can go ahead and make y the subject here, which is going to be r sine theta. So we can square both sides here, and we can square both sides of this as well. And then after doing that, then we shall just make the substitution here. We substitute for x squared, and then we also substitute for y squared in here. So if we do that, we should be able to come up with the result of r squared cos squared theta plus r squared sine squared theta equals to r squared. Okay, so of course we see this is common, it can cancel out, and then we have cos squared theta plus sine squared theta equals to 1. So we have a series of other results which we can get from this. The first one is if we decide to, let's call this maybe equation 1. If we get equation 1 and then we divide it by cos squared theta, then we should be able to get cos squared theta over cos squared theta plus sine squared theta divided by cos squared theta equals to 1 over cos squared theta. Okay, so we know this is 1, and then sine over cos, if you're familiar with these trigonometric properties here, we know that sine over cos is tan, but since everything is squared, so we have tan squared theta, and then 1 over cos is sec, and then since everything is squared, we have sec squared theta. So this is an important result, okay, which we shall use in the course of our study here. So another one we can say is if we divide equation 1 and then we divide by sine squared theta, then we have cos squared theta over sine squared theta plus sine squared theta divided by sine squared theta equals to 1 divided by sine squared theta. We know cos divided by a sine is cot, and then if we square, everything is squared, so it is the cot squared of theta, and then this is 1, and then 1 divided by sine is cosec, and then this is cosec squared theta. Again, another important result which is going to be handy. Okay, so we have that, and yes, this one here. Okay, those are the important results we are going to use. Alright, now armed with that, we can go ahead and now see how we can work out a problem if we are faced with integrating a problem which has all the powers of sine or of cos. So basically what we are simply going to do is going to make a series of substitution, either this one here, equation 1, or in equation 2, or in equation 3. We'll make a series of substitutions, and then we shall also use the property we learned last time of integrating by recognizing the presence of a function and its derivative. So here we look at an example. As usual, all these examples are taken from the Pure Math book, okay, book 2. Yeah, so you can find everything in there. So I'll simply, in this video, I simply give you an idea, and then you can please work out the rest of the examples and try out as many problems as you can. If you have any problem, you can just put it in the comment section. I'm sure there are people who help you if I don't see it first. Okay, so let us look at an example here. We have sine to the power 5 sine x raised to the power 5. So this is what we want to integrate. So in here, the trick is of course we see this is odd. Okay, so we just split it. What we are going to do is we are going to split it as a product of an even. Okay, so we shall see a product of even. Okay, and then we have here sine x. What is this? Okay, sine x dx. All right. So since this even power here, we can make a substitution. Why? Because we have seen from here, or we have been reminded that cos squared plus this cos squared plus sine squared equals to 1. Therefore, we know, or we can see, that sine squared x is going to be equal to 1 minus cos squared x. But this is sine to the power 4. So if we have sine to the power 4, it simply means that we are going to square this. That will be sine to the power 4, and square this as well. Okay, so I know we can expand the right hand side very easily. I trust you guys. So if we expand that quickly, I hope I don't make a mistake. If I make a mistake, you can always put in the comment section. Okay, so this is going to be 1 minus I think that is 2 cos squared x, and then this should be plus cos to the power 4x. Okay, yes, if no mistake, that is what we should have. And we multiply this. Remember, we have this sine x here, then dx. Okay, I don't know, for clarity maybe we can split this. Okay, but if you become experts, well, you don't need to split this. You can work this first time, but for the sake of everyone else, we shall decide to split this, and then we have this sine x dx. So term by term here, we know that the integral of sine x is simply going to be negative cos x, right? Okay, maybe for those who are not familiar, we can start with the reverse process. So we know that if we differentiate, okay, since the integration is the reverse of differentiation, we know that once we integrate cosine of x, we get negative sine x. Okay, so precisely if we integrate negative cos of x, we get sine of x. Okay, so that means that if you carry out the reverse process, differentiate with respect to x, integrate with respect to x, of course we get now the result that negative cos of x, okay. Okay, I always like to start with whatever I want, whatever I'm thinking as the unknown on the left hand side. So we integrate both sides here and then start with the right hand side. So we shall say that now therefore we know that if we integrate this, then we get negative cos x plus our constant of integration. We shall call that C1. So but we may leave this for now, then, because we integrate this, then we get a constant, then we integrate this, we get a certain constant, then we integrate this, then we get a certain constant, then in the end we have a constant plus a constant, and then we shall just write one big constant. Okay, so for now don't mind about the constants of integrations, we can just forget about them for now. Okay, so so we have said that this one here, the working is here, and then the result of sine x, we say that we integrate that sine x, let me just use a different color here. Okay, so the integration of that one there has given us negative cos x. Okay, then the next term here, the next term that we have, this term here, we want to integrate. We have a negative here by nu, so we shall just leave the negative and the constant alone. So let us just concentrate on integrating cos squared x sine x, okay, dx. So we recognize, if you have gone through many examples of the previous video, then you should be able to see that we have a function here, cos x. We shall have our function cos x, and then we have its derivative here. Okay, in other words, we know that we know we differentiate a cos, then we get a sine. So we see we have the presence of a function and its derivative, and then we go through the process we did last time of getting our function here and then raising it to the next power. Okay, so we have cos, which is squared there, so we raise it to the next power, which is power 3, and then we differentiate it with respect to the variable x. Okay, then what do we get here? According to the chain rule, we drop the power there, then it's cos squared x. Okay, then according to the chain rule, then we multiply it times the derivative of cos, which is negative sine x. Okay, I hope I haven't made a mistake here. So what is our interest here? We can say that now dx of negative 1/3, okay, cos cubed x should be equal to cos squared x sine x. So we put the integral and integrate both sides with respect to x. We come up with the result that cos squared x sine x dx equals to minus 1/3 of cos cubed x plus maybe another constant of integration here. So we know, so now we can come back here, and then we know we are going to substitute this part here. Okay, this part here, cos squared x sine x, this one here, this is what we have here. Okay, so we are left with one part, cos to the power 4x times sine x. So I guess we have to add another page here. What do we do? Yes, okay, that's good. So we have the integral. So lastly, we would like to integrate that last term, which is cos to the power 4 times sine x dx. Okay, times sine x dx. Again, we recognize the presence of a function, okay, in cos x here, and its derivative here, which is sine x. So the classic method, we are going to say that d dx of cos to the power 5x, okay, which is going to be, we drop the power here, we reduce it by 1, and then we multiply times the derivative of what is inside. When we differentiate the derivative, or when we get the derivative of cos, we get sine x, okay, and then we have that d dx of negative 1 out of 5 if we divide through by negative 5, and then we have cos 5x equals to cos to the 4x sine x. After that, what do? We introduce the integral with respect to x and start with the right hand side. Then we have that this x sine x dx should be equal to negative 1 out of 5 cos 5x plus a constant here. Okay, so again, this here, integral of cos to the power 4x sine x, this, we substitute the answer here. Okay, so if we do that, I think that's all we could do. So we do that, we say that the first result we have is a negative cos x. So we can write the solution here. We have negative cos x. Okay. What else? Then we have this negative 2 times the result we got here. So we shall have positive 2 over 3. Okay, plus 2 over 3 cos squared x. Okay. Oh, not cos squared, but it is cos cubed. Okay, this is cubed. And then lastly, this other term here, cos to the power 4x times sine x, positive. Okay, we got this term here, which is negative 1 out of 5 cos 5x, and then we add all the other constants, and then we have our one constant of integration here. So that is the answer, I suppose, if I haven't made a mistake. Okay, I'm not going to go through it because I just want to keep this video short, but maybe I'll go through it later on. If there is a mistake, you can please put it in the comment. And yeah, so I hope this has been well explained. Try to go through the video slowly, work it out, and then work out as many problems as you can. Basically, the idea is the same. If you have odd powers, what you simply try to do is try to do a simple transformation until you get a situation where you have an even power, because we can make substitutions for even powers in terms of whether it is cos, whether it is sine, or even whether it is this cotangent or this, cosec. As long as they are even powers, you can make the substitutions which you have, and then the rest follows as we have done here. The exercises should not be hard. I believe you should be able to work them out. Thank you, and see you in the next video.